Hey guys, welcome back to Algebra 2. Today we're covering 5, 6 inverse relations and functions, and we will be working in your workbook starting on page 260. So if you want to flip to page 260, that's where we will be today. So we'll be working on something called an inverse relation, and sometimes the relation is actually a function. So what does that mean? Well, inverse relations, we're going to look at them a few different ways. We're going to look at them numerically, we're going to look at them graphically, then we're going to look at them algebraically, where we have to do some algebra. So let's talk about numerically first. What are inverse relations? Well, inverse relations are when you switch the roles of the independent and the dependent variables. So in other words, you're going to switch the roles of the x and the y variables, also known as switching the input and the outputs. So numerically, what that means is if I were to have this original function, then if with an input of -2 and an output -6, input 3, output 8, input 8, output 2, input 13, output 7, if I switch those, like switch the -6 and 2, where the -6 becomes the input, -2 becomes the output, and I do that for all the points in the original function, that will give me the inverse. And for right now, we're going to call that an inverse relation because it may not necessarily be a function, especially if we look at this second example. If I call this first one the original function with input -3 to -4, 5 to 9, 8 to 7, and 10 to 9, each input has only one output, like meaning if I put -3 into the function, the only number that's ever going to come out is a 4. If I put a 5 into the function, the only number that ever comes out is a 9. You can put 5 in, you're not going to get anything else but a 9. If you switch those, I'll have my inverse relation. But then I look at these inputs and their outputs, and I see that if I put in 9, I'll get a 5 sometimes, and then at other times when you put in a 9, the output becomes a 10. So because you put in the same number as an input and got two different outputs, that would cause this inverse to not be a function. So even though the original was a function, the inverse may or may not be a function. So just keep that in mind. And so when the inverse is not a function, we refer to it as an inverse relation. So that's what you'll see numerically. Now let's look at graphically. Inverse relations graphically. So let's say if I look at this graph first, the blue graph, let's say this is the original function. I'm going to call this f of x. The green graph is the graph of the inverse. So f of x is a function, and then here is the inverse relation. Now, what do inverse relations look like graphically? Well, graphically, the inverse is a reflection across the line y equals x. So that is this line right here. If I were to take this piece of paper and fold it diagonally across this line, then f would match up. It would be right on top of the inverse. So graphically, the inverse is a reflection across the line y equals x. Now on the second graph, you have not seen y equals e to the x. That's something you'll see later, but I can go ahead and show you that y equals e to the x is a function. Its inverse would be this blue function, which again, we're not going to worry about its equation just yet. And that is a reflection across the line y equals x. The other thing to note is the inverse may or may not be a function. If you remember the vertical line test tells you if a function or if a relation is a function. If you can draw a vertical line and only hit the graph one time, then it passes the vertical line test and we do have a function. But right here, the inverse, if I were to draw a vertical line, I would hit the graph twice, which would make the inverse not a function. We'll see a little bit more about that later. And then algebraically, here's what we'll see before we do some examples. Algebraically, here's what we'll do. You'll be given an equation and you'll ask to find the equation for the inverse. So what you're going to do, these are the steps we're going to follow. If there's an f of x, you'll replace it with a y. So in this original equation, the y is already there. We don't have to replace everything. Done. Then you would switch the x and the y. So I would literally change this x to a y, change this y to an x. So that's what's happening here. Then you solve that for y. So it looks like they just wrote with the x on the other side. They added 5 to both sides. And then divide everything by 4 to get the inverse. Now, see this notation? That's inverse notation. So notation that you need to be familiar with, if f of x is the original function, you'll see it written similar to this. This is one way to write it. Another way, f, and the -1 looks like an exponent. This is notation for the inverse function. And we read it the way I would say it out loud. I would say f inverse of x. So you see this notation, you say f inverse of x. You do not say f to the -1 of x. I know it looks like an exponent, but that's just notation to show that it is the inverse of x. All right, so these are the types of examples we're going to have today. Let's go ahead and look at example 1. So example 1 has a table. We need to identify the inverse, and then is it a function? So here's the table that gives me the original. To identify the inverse, I'm going to switch all the x's and the y's. So when the x was -1 and the y was 9, now my x will be 9 and y will be -1. So then the 0.07 is now 7, 0. 1, 5 is now 5, 1. 2, 3 is now 3, 2. 3, 1 is now 1, 3. And 4, -1 is now -1, 4. So this is the inverse relation. And then they ask me, is it a function? So does every input on the inverse have only one output? Let's see, -9, or sorry, if I put 9 in, I'll only get -1. If I put 7 in, I'll only get 0. If I put 5 in, I'll only get 1. 3 in will only give me an output of 2. 1 as an input only gives me an output of 3. And -1 as an input only gives me an output of 4. So this is not only an inverse relation, we call this an inverse function. All right, so example 2. Find the equation of the inverse relation. I want you to change your notes. It's the one in your notes is fine, it's just not as exciting as this one. So change it to f of x equals x squared minus 4. So we're going to write the equation of the inverse first. All right, so f of x equals x squared minus 4. Remember that first step was to replace f of x, if there is one in the problem, with y. So I'm going to replace the f of x with a y to have y equals x squared minus 4. Okay, step 2. You're going to switch the x and the y. This is what gives you the inverse. So from here on, I'm going to be working in red because now I'm going to be working with the inverse equation. So switch the x and y. X equals y squared minus 4. Step 3, solve for y. Let's see. So solve for y, so I'll add 4 to both sides. And solve for y, take the square root of both sides. Y equals, when I'm solving an equation, I need a plus or minus square root x plus 4. And then number 4, use inverse notation. So if my original was f, then my inverse is f inverse of x equals plus or minus square root x plus 4. Okay, so then part B says, how can I use the graph of f to determine if the inverse of f is a function? Explain your answer. Okay, so let me graph these. Okay, so before we look at how can I use a graph to determine if the inverse is a function, I do want to point out a couple things about domain and range of each graph. So I have the graph of f and the graph of f inverse. So let's identify domain and range for each. So the graph of f has a domain of negative infinity to infinity. It extends forever and ever to the left, forever and ever to the right. It has a range of negative 4 to infinity. Okay, now let's look at the domain and range for the inverse. The domain, let's see, it only goes from this all the way to the right. That's negative 4. And then for an ever and ever to the right would be to infinity. And then the range, let's see, low up to high, looks like it's going forever and ever in both directions, bottom and top. So range would be negative infinity to infinity. Now, earlier in the lesson, I did say that the domain and range were switched, but I do want to point out the domain of f switched to the range of f inverse. And the range of f is now the domain, that's not the best color, the domain of f inverse. So the domain and range switch. Just pointing that out. Once again, domain and range switch. And that will come up on your homework, on your test. So just keep that in mind. So I would definitely write that down. Domain and range will switch on you. Okay, so how can I determine if the inverse of f is a function? Okay, well, let's talk about f original for a second. Let me draw a line. Red line, yeah. Let's draw a straight line. Straight line, make a blue one. No, straight line. Okay. Okay, so here's a vertical line. The vertical line test tells me if something is a function. So if I hold this vertical line over the graph at any point, trying to drag it around. Looks like it hits my function, the blue part, only one time, but it's hitting this red function twice. So that indicates to me that the inverse is not a function. And that's okay. The inverse is not a function. The inverse graph hits this vertical line twice. But I can get away without even graphing the function. I can just look at the original function. I can do something called the horizontal line test on the original function. So if I were to draw a horizontal line and then drag it across the original function, you see how the horizontal line hits the function twice? If the horizontal line hits the function twice, that means the inverse will not be the function. And here's that written out, the horizontal line test. The inverse of a function f is a function if and only if no horizontal line intersects the graph of f more than once. So here's an original function. You draw a horizontal line. That tells you that whenever you do the inverse will be a function. Here is a parabola, kind of like the one we just did. If you draw a horizontal line, the inverse is also a function. Okay. Now, if the inverse relation is not a function, we can make it one. And we can make it one by doing something called restricting the domain. So that's in example 3. All right, so example 3 says we're going to find the inverse of each function by identifying an appropriate restriction on its domain. So part A, we have the function f of x equals 8x plus 16. So it would be best if we think about the graph of this, and I'm going to go ahead and tell you that if we look at it in factor form, it'll be easier to think about the graph. So here's f of x. F of x is, let's see if I factor this, it'll factor into an x and an x, plus 4, plus 4. So f of x equals x plus 4 squared. Okay, so let me sketch the graph of that function. So if I look at the graph, let me just make sure I'm still recording. Yes, okay. If I look at the graph of f of x equals x plus 4 squared, and if I draw a horizontal line through it, horizontal line would hit the graph twice. That would mean the inverse would not be a function. But this problem wants me to make the inverse of a function by identifying an appropriate restriction of its domain. So let's talk about this function. It has a domain of negative infinity to infinity, and then a range of 0 to infinity. Okay. If I do something called restrict the domain, which means don't graph the entire parabola. So instead, maybe I only want to graph this part of it, the part on the right side. Now there's more than one way to restrict the domain of a function. Usually if it's a word problem, it's the context of the situation that influences the domain, but if it's just like a general formula, then I get to pick how I'm going to restrict the domain. So I'm going to restrict it to this right side. So instead of having a domain of negative infinity to infinity, I'm going to change that to have a domain of from here to infinity. So that's 1, 2, 3, negative 4. So that way, whenever I find the inverse, I'll switch the domain and range, and I know that it will have a domain that was the range of 0 to infinity, and then a range that was the domain of negative 4 to infinity. So that's how I can restrict the domain. So usually when it's a parabola, you just pick one side and only do one side of it. All right, so let's find the equation of the inverse. So to find the inverse, I'm going to change this f to a y. Then I'm going to switch the x and the y. So x is now y. And then I am going to solve for y. So we're going to take the square root of both sides. Plus or minus square root of x equals y plus 4. So then subtract 4, and the plus or minus square root of x minus 4 would be y. Now, it's not going to be plus or minus because I've restricted the domain, so let's see what happens. All right, so if I graph that, that's down for 1, 2, 3, 4. 2. All right, so it looks like the inverse, if I leave it like this, it's not going to be the function. But we restricted it so that the domain goes from 0 to infinity, and the range goes from -4 to infinity. So from -4 and then up means I'm going to delete this bottom part. So let me erase that bottom part so that the range of my inverse only goes from -4 to infinity. There we go. So there's my inverse. That's how I make my inverse relation into a function. So I can say that my inverse function, the equation for it, I can put my pen, would be, since it's going up, the positive square root of x minus 4. If I had chosen the one that went down, I would choose the negative square root of x minus 4. All right. Then in example 3b, we can skip example 4. Find an equation of an inverse function, and then we'll sketch a graph. All right. So here's f. So sketch the graph of f by drawing points on the graph. So that means I need to take the parent function, shift it to the left 1, reflect it across the x-axis and up 2. So let me go ahead and do that. Okay, so here's the graph. Just sketched it on Desmos. Sketch the graph and then verify that the inverse will be a function. Well, if I were to draw a horizontal line through any part of this graph, I would see that the graph only hits the horizontal line one time at any point. So since this graph passes the horizontal line test, the inverse will also be a function. Okay, so part, where's my pen? Where's my pen? Okay. So I can say since f of x passes the horizontal line test, and I'm going to abbreviate that HLT, the inverse, or I can say the inverse function, or f inverse, is also a function. Okay, will be a function, and then write an equation for f inverse. All right, so let's write an equation for f inverse. I'm going to replace the f of x with a y. Y equals 2 minus the cubed root of x plus 1. Then I need to replace the x and or switch the x and the y. So now I'm writing in red. That means I have the inverse. X equals 2 minus the cubed root of y plus 1. Then I'm going to solve this for y. So I'm going to subtract both sides by 2. X minus 2 equals the negative cubed root of y plus 1. Divide both sides by the negative. Negative x plus 2 equals the cubed root of y plus 1. If I want to undo the cube, I can cube both sides. So the negative x plus 2 cubed equals y plus 1. And then I can subtract 1 on both sides to get negative x plus 2 cubed minus 1 equals y, which means that my inverse function is negative x plus 2 cubed minus 1. And I'm not going to cube out that binomial because that would be a lot of multiplication, so I'm just going to leave it the way that it is. Verifying inverses. So if you see this word verifying inverses, that is your cue to use something called use a composition. So there is a rule that you can use to verify inverse functions. It's if you do f of g and you get x, and you do g of f and you also get x, then those functions are inverses of each other. So I'm going to color code again, just like I did in the previous. I'm going to say that f of x is in red, and I'm going to put g of x in blue. So first I'm going to work on f of g of x. So I need f of g of x, which means that I'm going to copy down the f function, but instead of an x, I'm going to put a parentheses, and then inside the parentheses goes the g function, x cubed minus 1. And I'm going to simplify everything I have. So let's see, x cubed minus 1, oh, there's a plus 1 right here, that's plus. X cubed plus 1 minus 1, those 1's cancel out, and I just have the cubed root of x cubed. And the cubed root of x cubed is x. So for f of g of x, I got x. Yay. But I'm not done, because f of g has to be x, and g of x also has to be x. G of f also has to be x. So let's find g of f of x. Which means I'm going to take my g function, I'm going to copy it down, but instead of x, I put parentheses, and then instead of the x, I replace it with f. So the cubed root of x minus 1. Then I'm going to simplify everything. All right, so when I cube a cubed root, those just cancel. And then I have x minus 1 plus 1, and x minus 1 plus 1 is x. So for g of f of x, I get x. So since f of g of x equals x, and g of f of x equals x, then I can say that f and g are inverses of each other. All right, and then example 6 has me rewrite a formula. So example 6, the manufacturer of a gift box designs a box with length and width each twice as long as its height. So let me pause right there. Whenever we have a box, we always have length, width, and height. And usually we use LW and H. Okay. But it says width and with length and width each twice as long as the height. So that means the width is twice as long as the height, and the length is twice as long as the height. So the first thing that they want me to do is to find a formula that gives the height of the box in terms of the volume V. Okay, well I don't have a formula for height, but I do know that the volume of a box is the length times the width times the height. And I also know that the height, the length and width are 2h. So I'm going to replace length and width with 2h. So volume is going to be 2h times 2h times h. And if I simplify that, volume is 2h cubed. Did I do what they needed me? Find a formula that gives the height. Okay, so no, that means when it says gives the height, that means they want the formula h equals. So I need to take this and I need to solve it for h. So I can divide both sides by 2. V over 2 equals h cubed, and cube root both sides. So h is going to be the cubed root of v over 2. Done. Okay, so I found a formula that gives the height in terms of volume. In terms of volume means v is the only other variable in the formula. Okay, then give the length of the box if the volume is 640 centimeters. So I got to work back to the length. But I do know that the volume is 640. Okay, so let's do this. Let's take this formula. H equals the cubed root of v over 2. So h equals the cubed root of 640 over 2. 640 is volume. H will be the cubed root, 640 divided by 2 is 320. And so I think we do get to round on this one. So h is approximately, if I take the cubed root of 320, I get approximately 6.8399. But I'm asked for length, and I know that the length equals 2 times h. So length will be 2 times whatever I found for h. So length is approximately 13.6798 centimeters. Nope, just kidding. I made a mistake. Sorry, and if I try to edit it together, it's going to take me longer than it would to make a whole new one. So I did make a mistake. So let's go back here. Sorry, there's a mistake. So I'm going to erase this. I multiplied wrong. So I'm going to pause and erase. Okay, so 2h times 2h times h is not 2h cubed. It is 4h cubed. So volume is 4h cubed. Okay, so then what do I need to do? I need to solve that for h. Divide both sides by 4. And then take the cubed root of both. So h is going to be the cubed root of volume over 4. All right, so there's my formula for height in terms of volume. Then I need to find the length, but I only know the height, and I'm given that the volume is 640. So I'll start off by substituting in 640 in for volume. So the height is the cubed root 640 divided by 4, which would be the cubed root of 160, which is approximately 5.4 0.4288. But then we know that the length is twice the height. So the length is 2 times whatever I got for the height. So length is approximately, because I'm still rounding here, 10.8576, so 8 centimeters. There we go. Sorry about that.